Okay, this is video 3, just continuing on. This shouldn't take that long. Let's see. All right, so question I and J takes a little bit more. Wow, what a mess. This chalk is building up. I'm going to have to clean this board. Oh, boy. I'm putting a little jacket over in front of my computer. Okay. So we'll get all this dust on it. Let's see here. Good grief. Okay. All right. It says here, what effect will a deep... Oh, we did that one already. Oh, no, I didn't do that. What effect will a decrease in temperature have on the standard free energy change? Would it become more negative, less negative, or remain unchanged? Okay, letter I. What effect will a decrease in temp have on standard free energy change? Would it become more negative, less negative, or remain unchanged? Explain your answer. The best way to do a question like this is to go to the equation, agatas, and then plug these things in. All right. We know delta H, and then we have T times delta S. All right, so delta S is negative, and delta H is negative also. And remember, we calculated delta G to be negative, right? Yeah, it was negative overall. Okay, delta G, when you get all that together, it was negative negative 285, right? Negative 285. Okay, so a negative number, ends up being a positive term in here. Okay, so here's the deal. A negative times a negative is positive, right? So we know that. I could just take that away for a minute. Negative and this. So what we're saying is that since the overall delta G is negative 285, then, let's put the T there. Since overall delta G is negative 285, that means that this is greater than this. So we know that delta H term is greater than the T delta S. T delta S. We know that because since the overall number is negative, then when you subtract, since it's minus, the magnitude of that, this is larger than that. So it says, what effect will a decrease in temperature have on the standard free energy? So if you lower the temperature, if you make this a smaller number, then you're just going to make the delta G become more negative. Okay? So it just says, will it become more negative, less negative, or remain unchanged? And then it says, what is it? What's it going to? Well, that's all it says in the question. That's all you have to answer. Since delta G is negative 285, you could actually plug in the numbers if you wanted to put them there. But we know that delta H is a negative value. And we know that this, when you multiply it, well, it's a negative value because delta S is negative. But minus a negative means plus. Okay, so if you lower the T value, you're not going to do anything different. It's going to become more negative, in fact. This number will go down, lower, north to 0. So delta G becomes more negative. That's all I have to say. Now, because it's more negative, I added on, that means it's going to be in the forward direction. It's going to be more spontaneous in the forward direction. That could tell you a little something there. Okay, now for letter J. This is probably the most important one. I'm going to try to remember this too, because I'm starting to think as I do this review, some people are going to know are going to be fine with this whole thing. But here's a new one. This is a new thing that I have not mentioned. Letter J. I'll try to remember that when I write the video assignment. Hey, you might not even really need to watch this video, I'll say. You can just do these worksheets, but skip ahead to the letters you need help on. But letter J, you need this. J, 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 J. Okay, it says, determine the temperature at which equilibrium exists. Okay, that's the first thing. Now, we did something like this in a previous video. If you did see it, you may not have. So to determine determine the temperature at which equilibrium exists. Okay. Equilibrium, we talked about this in Thermo last semester too. But at equilibrium, delta G equals 0. Okay? So it means it's not driving forward, favoring, or backward. You finally get to a point where it is 0. Okay. That would be a true equilibrium. So if delta G is 0, then just solve for the temperature. And so you put in negative 285 kilojoule per mole minus, we don't know T, but we know delta S is. Now be very careful. I always say it, 87 over 1,000, because it has to. It's in joules per Kelvin, but that way it becomes kilojoules per Kelvin mole. And now we just did the math here. So it looks like you'll get 285 will become positive 285 on this side equals 0.087 T. 0870 actually. Did I put a 0 on that number? Oh, I did. I didn't even from the beginning I didn't see it was 87.0. That's another sig fig. Okay. So then divide them both by 0.0870. 0.0870. And it says the temperature is equal to 3280. Oh boy. 80 Kelvin. Okay. So here's what they can do on AP. They could give you a problem, equilibrium. And again, normally what happens is you do an equilibrium problem the way we've been doing all the math calculations. Find Ka, or they give you the Ka, find the molarity of this at equilibrium, or pressure of this gas at equilibrium. You know, you do all that, the K expression, la la la. You do all that math. Then they probably ask you one or two things of this paper. They're not going to ask you the whole thing, okay? But this is everything they can work in with Thermo if they want to add Thermo to equilibrium. But this is probably one of the most important questions of essay. If they just said, find the temperature at which equilibrium exists, that's all you got to do. Just solve for it. That's actually the easiest question. But they don't always say that. Sometimes they say what you see in J, the second part. At what temperature will the value of the equilibrium constant be less than 1? At what temperature equal to 1? At what temperature greater than 1? Assume delta H, delta S are independent of temperature. Okay. They're only going to ask you one of these questions. So they might say, find the temperature at which equilibrium exists. We did it. Or if they say, find the temperature at which K equals 1. Well, when K equals 1, delta G equals 0, and that's going to be the temperature at 3280. Here's what you should do if you want to be safe to cover all grounds. If they ask you anything in equilibrium about temperature, at what temperature will this be non-spontaneous? At what temperature will this reaction become spontaneous? At what temperature will anything like that? First, find the temperature, and I'm going to tell you how to make a little chart. So first you use delta G, you find the temperature. Now, if that was the end of the question, you're good. But sometimes they want more. So look at this and I'll show you. Okay, here's a little chart that I like to make. All right. At equilibrium. All right, well, I'm going to worry about that. Okay, all right, if delta G equals 0. Okay. Delta G is equal to 0, then that means K will equal 1. All right. When delta G, temperature equals, you know what? I made my chart wrong. I wasn't looking at my paper. I'm trying to do it from my memory, but now I realize the order. All right. At temperature equal to 3280. I'm having a problem with my 8. Okay, yep, 80. My chart's going down. When the temperature equals 3280, delta G equals 0 and K equals 1. It's at equilibrium. Okay, if you wanted to say that, you could. Okay, at temperature greater than 3280, okay, what's going to happen if you're more than that? Now, to answer this question, like I showed you before, Because remember, they're only going to ask you probably one question on this paper. Maybe two. But they almost all use this equation. So here's what we know. We know, in fact, I might even put the numbers in. We know that when that's 0, what was it, 3280? Okay, when that's 0, then negative 285 minus, and this side is 3280 times, 87.0 over 1,000. Okay, so we know that this equals this. These two things equal 0, all right? When you have 3280 there, it is exactly 0 equals 0, okay? So at equilibrium, temperature is 3280. What would happen if I put a temperature greater than 3280? Well, now it's kind of like I showed you, and that's a negative number there, by the way. All right, it's kind of like I showed you a moment ago. So think about this. Minus a negative is like saying this number becomes positive over here. So if this value of T goes up, then what's going to happen to G? It's not going to be 0 anymore, right? Like, say it went up to 3281 or whatever, just went up a little bit. Suddenly, now delta G will become positive. We don't have to calculate it, but we know that delta G is going to be a positive number. If that number goes up, if temperature goes up, if I increase this, then delta G becomes positive. Right now it's 0, they're equal. But if that goes up, it becomes positive. So at temperature greater than that, you can say delta G is greater than 0. Or you can say delta G is positive. A positive number. Okay, now if delta G is positive, then think about what's going to happen to your K value. And we'll get that in a second. I'm going to show you that in a minute. But first, let's do this section. Okay, if delta G is greater than 0 when that temperature goes up. At a temperature less than 3280, now delta G must be negative. Okay, let's see if that would work. So if that number were smaller, well, now the negative value becomes greater than that. And so it's going to be at lower temperatures, delta G will be less than 0 or negative. Delta G is negative. I'll do my chart this way. This chart answers all the questions. I mean, we're talking about like you want to make a 5 on the AP exam. Okay. Uh-oh. I didn't mean to do that. But, well, it doesn't matter now. I kind of showed it to you already. So now every problem can be different because like what if that were negative and that were positive? Or, so you got to make a new chart and think it through each time. But if in this case, less than 3280, delta G is less than 0, or delta G is negative. One or the other is all you got to say. Okay, now what happens to K? This is what we do. In the ideal standard world, your K, Kc or Kp, would equal CO2 over CO times O2 to the 1/2. Or if it were a Kp, it would be, the pressure of CO2 over pressure of CO times pressure of CO2 to the 1/2. Remember that. Well, here's the deal. If it were an ideal, perfect equilibrium world where delta H and delta S were not dependent on temperature, then everything was standard. Standard temperature, standard pressure, standard molarities are all 1, 1, 1, 1. Standard pressures are all 1, 1, 1. Guess what? If everything were perfect, K is equal to 1, right? So that's that situation up here. 1, 1, 1. 1 over 1 times 1 to the 1/2 power is 1. 1 over 1 times, that's all it is. So that's why they get the idea of, theoretically, K would equal 1. Well, here's the deal. If delta G is greater than 0, it's positive. Positive would mean, will it be shifting in the forward or the backward? What's spontaneous? Positive in equilibrium means the reverse is going to be spontaneous. It's going to be heading that way. So as it heads that way, what's going to happen to the top number? Top number is going to go down, and the bottom is going to go up. So if delta G is greater than 0, or if delta G is positive, then the top number is going to get smaller. It's going to be spontaneous reverse until a new equilibrium is reached. Okay? It's going to go that way. This number is going to go down, and those are going to go up, up, up. So this, which was 1, gets to be less than 1, and those get greater than 1. So K is going to be smaller. It's going to be less than 1. The new K will be less than 1. And you could even describe it that way. They don't even really ask you to describe it. But if they did, they'd say, because the numerator will decrease and the denominator will increase, therefore the new K will be less than 1. When you get to the new equilibrium, your K value will be less than 1. Okay. All right. If the temperature is greater than 3280 and it's negative, that means the forward is spontaneous. So that means you're going to keep going that way. And what that tells you is that the bottom, CO and O2, they're now going to go down, and the top part is going to get higher, go up. Therefore, K will be greater than 1. So there it is. There's the whole thing for you right there. That little chart. And as I said, normally on AP, they're only going to ask you one of these questions. And so if they ask you anything about find the temperature, if they say find the temperature at which equilibrium exists, or find the temperature at which K equals 1, or find the temperature at which this reaction becomes spontaneous. Okay, well obviously it will be spontaneous. If delta G equals 0, well you're at equilibrium. Now they're going to say spontaneous in the forward or backward direction. But technically anywhere it will become non-spontaneous. You could say that. That's a better way to say it. Here it's like nothing's spontaneous when it's at equilibrium. But now, anywhere in this range, any temperature below that, it will be spontaneous. Any temperature above that, positive, it will not be spontaneous in the forward direction. Okay, what was I kind of interrupted myself. Oh, if they only ask you for the temperature at which equilibrium exists, temperature at which K equals 1, find it. That's all you do. You just find it. It's easy. You're done. But if they say, at what temperature will this become non-spontaneous? They could just say that for the first question. Find the temperature at which this reaction will be non-spontaneous. Well, first, I got to find the temperature. Oh, that's 3280. Then, non-spontaneous, what does that mean? I would advise you make the whole chart and you say, non-spontaneous in the forward would be that one. Okay? At any temperature above 3280, it will not be spontaneous in the forward direction. Okay? That's how you do it. Okay, or what temperature would it be spontaneous? It'd be that. Or would delta G be negative? Okay, that answers everything. I'm just telling you. Okay, and the last question, what is the standard enthalpy? Oh, this is a simple. I'm not even going to do. What's the enthalpy change when 3 moles of oxygen react with carbon at 1 atmosphere and 25 to produce CO? So remember, all you're doing here is you're just using, I said I wasn't going to do it, but I can just set it up. This is a stoichiometry problem, no thermo at all. So at what, let's see. If you have 3 moles of O2, it says what will be how much heat's going to be released or absorbed or involved. Well, 3 moles of O2, all you do is you just say, okay, from moles of O2, I can go to 285 kilojoules of heat. Now, technically, it's negative. I mean, that number can be used. It matches the stoichiometry. Let me just take it out of there. Negative 285 for every 1/2 a mole of O2. So just divide that by 1/2, and it's negative 1710 kilojoules of heat will be released. That's just a stoichiometry that I threw in there. Okay, now, wow, you are now able to do all of number 3, the whole big page, and problem. And then I'll probably do the other example B for you to get the last bit of that. So this is a better video. I think this is better than everything we went through. Whew. Everything that they can ask you about thermo with equilibrium is here. All right, I'll see you.